Hi, this is Dr. Green, and we are looking at some examples for homework set number 4. So each time you work through an example on the video or view an example there, then I would recommend you go back and do the corresponding problem in the homework. You can skip over things that you know how to do. You can rewind things that you don't understand. So let's go ahead and get started. There's only 15 problems instead of 20 in this homework set. Some of the problems are a little bit longer, but we can make it. So in this first problem here, they give us a graph of a quadratic function, so a parabola, and they want us to select the equation here from this list. So well, we see that this parabola opens upside down, so we know right away that it's got to have a negative in front of it. So this positive x squared, that one's out. And here this one is the negative of x minus 1 squared. So that's a possibility. X squared minus 1, so that's x squared, right side up function, shifted down 1, that's out. And then negative x squared minus 1, so that negative x squared, that's a possibility. So it's either B or D. So it's flipped upside down, that's going to be the negative out in front, and then it's shifted to the right 1 unit. So it's right 1 unit, and then it's flipped upside down, so reflect over the x-axis. So if you shift it to the right one, that means that you're replacing x with x minus 1 on the inside. So this is negative x squared, and this is the negative x minus 1 squared. So this x minus 1, that is a right shift of 1. And then this negative flips it upside down. So it's got to be choice B. So choice D here is going to flip it upside down first, and then this minus 1 on the outside shifts it down 1. And that's not what we've got going on. We're shifting to the right one, so that's an inside subtraction. And remember, the inside is a liar. It does the opposite. This is a negative 1, and it shifted it positive 1. Number 2, we are finding coordinates of the vertex here, of the parabola. So we got x and y coordinates of the vertex of this parabola here. So remember that the x coordinate is given by negative b over 2a, where our a here is going to be negative 3, b is going to be positive 6, and c is going to be positive 1. So negative b over 2a is going to be a negative 6 over 2, and then our a is negative 3. 2 times negative 3, which is negative 6 over negative 6, that's 1. So that's our x value is 1. And then our y value, we'll just plug that 1 back into the original function. So negative 3 times 1 squared plus 6 times 1, and then plus 1. So just plug the 1 back in here for x. So this is a negative 3, positive 6 is positive 3, plus 1 more, that is a positive 4. So our vertex here is 1, 4. And let's see, number 3, we have a quadratic function that's given to us 1 minus x plus 2 quantity squared. And we're going to use vertex and intercepts to sketch the graph first. Okay, so the vertex here, well, our f of x is 1 minus x plus 2 quantity squared. We could write that as the negative of x plus 2 quantity squared, and then plus 1. And then our vertex, remember, in standard form, this is going to look like this. It's the negative of x minus negative 2 squared plus 1. And then our vertex is given, here's the x coordinate and the y coordinate of our vertex, negative 2, 1. So remember, this is the standard form for that parabola. So negative 2, 1. So we are going to go 2 to the left and up 1. Right there is our vertex. And now intercepts here, for the x-intercept, you're going to set the y-coordinate, which is the whole function, equals 0. So we're going to set the 1 minus x plus 2 squared equals 0. And let's go ahead and bring this negative over on the right as a positive. So we got x plus 2 squared and is equal to 1. So now they're both positive, and we want to take square roots on both sides to undo that square. So then that's going to give us x plus 2 is going to equal positive and a negative square root of 1 plus or minus 1. And bring the 2 over as a negative. Your x is going to equal negative 2 plus or minus 1. Negative 2 minus 1 is negative 3, and negative 2 plus 1 is negative 1. So those are our x-intercepts where it hits the x-axis. So negative 3 here and negative 1 on the x. And then the y-intercept, for the y-intercept, you're going to set x equals 0 instead of y equals 0. So set our x equals 0, and that tells us then that our y-coordinate, which is our f of x here, is going to be 1 minus 0 plus 2 quantity squared. So that's 4. This is 2 squared root of 4. 1 minus 4, negative 3. So it hits at negative 3 on the y-axis, which is down there. And then they want us to go ahead and sketch that graph, and so we know this is the vertex. We know it opens downward because that minus sign out in front. So it looks something like this. Okay, so there's our graph. And then also remember, you can think of this as, okay, so you've got the basic graph is your x squared graph. The x plus 2 shifts it to the left 2 units, so that was this shift. And then the plus 1 here shifts it up 1 unit. So you go up 1, so to the left 2 and up 1, and that lands the vertex here. The negative flips it upside down, so now it's upside down. Okay? So you got a left-right shift, up-down shift, and a flip upside down. Axis of symmetry is given by the x-coordinate of the vertex, which is negative 2. That's also the negative b over 2a, because that also gives the x-coordinate of the vertex. And so that's our axis of symmetry, and that is right here. So notice that the graph is symmetric around that line x equal negative 2. It's a mirror reflection of the line. Domain and range. So domain is all the x values that are hit. So this thing goes to the left and right to minus infinity and infinity. So this is negative infinity to infinity. And then your range here, all the y values that are hit, well, no y value above 1 here is hit. So everything below is hit. So negative infinity, because this keeps going down, smaller and smaller y values. But up to and including 1, but nothing higher. So close bracket on 1, open at negative infinity. So that one's all set. So in this next example, we are looking at a ball that's thrown upward and outward from a height of 5 feet, and the equation of it's given by this function, negative 0.7x squared plus 3.5x plus 5, and x is the ball's horizontal distance here, and that's in feet from where it was thrown. We want to know, first of all, what is the maximum height of the ball? Okay, so that ball, you throw it, and it's going to look something like this. And come down and hit the ground, and you're starting here from a height of 5 feet. So the maximum height's going to occur up here. That's going to be at the vertex for that parabola. It's a parabolic path. So maximum height occurs at the vertex. So here's our equation. Just brought that down from up above. So our A is right here. So A is negative 0.7. Our B is 3.5. And our C is 5. Actually don't need that in this part. But then the x-coordinate of the vertex, negative b over 2a. So that is going to be negative 3.5. And we're dividing by 2 times negative 0.7. And if you plug that in the calculator, you will get 2.5. So that's 2.5 feet. And then the y-coordinate, we want the y-coordinate to go with that. We just plug 2.5 in here. Okay, so negative 0.7 and multiplying by 2.5 squared. And then plus 3.5 times 2.5. And then add 5 onto the end. And compute that with the calculator and you'll get to 1 decimal place, 9.4. So it's approximately 9.4. So our vertex, 2.5, 9.4. The max height's given by the y-coordinate, 9.4 feet. And where does it happen? Well, it happens 2.5 feet from where it's thrown. How far does the ball travel horizontally before hitting the ground? Okay, so when it hits the ground down here, the y-coordinate's going to be 0. So what we want to do is we want to find when the height is 0. So that means take our f of x, which is our y-coordinate there, and we set that guy equal to 0 here. So that gives us a quadratic equation to solve. It doesn't factor, so we'll whip out quadratic formula. Right here I've written it down for you. So remember our a, b, and c. A includes the negative sign. So negative b is going to be negative 3.5 plus or minus, and I got a square root. B squared is 3.5 squared minus 4 times our a, negative 0.7. Give myself a little bit more room here. Let's see, negative 0.7, and then c is 5. And then all over 2a, 2 times that negative 0.7. Okay, and so plug this into your calculator and simplify that. And if you do, you will get negative 1.6 or 6.6. Okay, you're getting one negative and one positive answer. So this is to 1 decimal place, negative 1.6 or 6.6. So the 6.6 is out here, and the negative 1.6, that's back here. Okay, so it's going to be 6.6 feet. That's our answer for part B. So 6.6 feet before hitting the ground. And then the coordinates of that point where it hits are 6.6 comma 0. And then part C is to graph the function that models the path, and we're using this template here. So, well, we start from this point that's 5 feet above the ground. So 0, 5 right here. Got that point on the graph. And then we've also got the vertex point, 2.5, 9.4. So 2.5 and then 9.4. So that would be about right there. And then we've got the point where it hits the ground, which is 6.6 comma 0. So that would be about right here. And then we want a nice smooth parabolic arch that goes through those points. So it looks something like this. So that ball is going to increase in height for a while. It's going to reach a max height, and it's going to start coming back down, hit the ground 6.6 feet out. And number 5, they're asking us which function is a polynomial function with degree 4. So degree 4 means that the highest power in the polynomial function is 4. And so the highest power here is 3, so this is degree 3. Part B, that's degree 4, highest power is 4. C, this is degree 6, and this one's degree 2, highest power. So that's B. So not a whole lot of work to show there. And then number 6, they want us to use this leading coefficient test to see what the end behavior is for a polynomial. So here's our polynomial. It's an odd degree, and it's got a negative coefficient. So I summarized the lead coefficient test down here. So it's looking at that highest power term, the leading coefficient. If n is odd, then your leading coefficient is greater than 0, then it goes down to the left and up to the right. So that would look something like this. Like an S-shaped graph like that. Down to the left, up to the right. If your leading coefficient is less than 0 and n is odd, it goes up to the left, down to the right. So that would look like this. Something like that. Goes up to the left and down to the right. If n is even here, then you have the same behavior at both ends. If your leading coefficient is greater than 0, it goes up both ways. So that would be like with an x squared graph and positive x squared. And then if n is even here but leading coefficient is less than 0, it goes down to the left and down to the right. So that would be like a negative x squared. So that'd look something like this. So those are your possibilities. So we look at ours, and it's odd, so that's this column, and our a sub n is negative 2. Okay, so a sub n equals negative 2 is less than 0, and n is odd. Okay, so that is this case here. So it goes up to the left, down to the right. Up left, and down right. And let's see here. Fall to the left, fall to the left, rise right, rise left, fall right. That's what we want right there, D. Got it. All right, and then in number 7, we are considering this polynomial x to the 4th minus x squared. We're going to use that leading coefficient test again to determine the end behavior. Then we're going to find intercepts, state whether the graph crosses x-axis or touches it and then turns around. Then we're going to find y-intercept. Then we're going to determine if we got y-axis symmetry, origin symmetry, neither, and then find some extra points and graph it. Okay? So let's go ahead and jump in here. So part A, lead coefficient test. So our leading coefficient is 1 because it's 1x to the 4th. Okay, so that means that if we go back up into our table, our n is 4, which is even. So we're in this column. And this is our a sub n. Our leading coefficient is 1, which is greater than 0. So we were in this first row. So it goes up left and up right. Okay, so an is greater than 0, n is even. So we rise left and right. And then for part B here, x-intercepts. So you want to set y equals 0. So this whole thing is y. So we set that whole thing equals 0. We have a common x squared that we can factor out of there. X squared will be left here, and just 1 is left there, negative 1. So that means that either, since this product is 0, either that first part is 0, x squared equals 0, in which case x equals 0, or the second piece is equal 0, x squared minus 1 is equal 0, in which case bring the 1 over as a positive, x squared equals 1, take square roots on both sides, and that means x is equal to plus or minus 1. So those are places where it hits the axis. And then we want to tell, does it cross or does it touch the axis and then turn around at the point? And remember that the way that you determine that is by whether or not you've got a double root at that value. So x equals 0, for example, is a double root because x squared, it gives x equals 0 twice. So here, x equals 0 is a double root. And the double roots are where it touches and then turns around. So there it just touches. But x plus and minus 1, those are both single roots. Okay, so x equals plus or minus 1 are where it crosses. And then part C, y-intercept. So you set x equals 0, plug that in and get the y that goes with it. So we plug that in here and here. So that's 0 to the 4th minus 0 squared, which is equals 0. So x and y-intercept are both 0. And then part D, we're looking at symmetry here. So remember, for symmetry, what you do is plug negative x in for x in this original equation. So that's going to be negative x to the 4th power minus negative x squared. And then even powers on a negative just give the same thing. So this is just x to the 4th minus x squared, which is our original f of x. So f plug in negative x is the same as f of x. That's an even function. That's y-axis symmetry. And that's the only symmetry we've got there. And then part E, we want to, use turning points to check whether it's drawn correctly after we sketch it. So let's go ahead and sketch, and then we'll use the turning points here. So let's first plot some of our important points for the graph. So we have our x-intercepts, which are at 0 and plus or minus 1. So down here is the x-axis. This is x-axis. And so we're going to hit at 0, and then out here at 1, and then here at negative 1. And then let's see here, the y-intercept is at 0, so we've already got that plotted. And now we'll go ahead and plug in some points here. So we know at x equals 0, it's equal to 0, and at x equal 1, it's equal to 0, because those are x-intercepts. Let's go ahead and plug 0.5 into our x to the 4th minus x squared. So it's 0.5 to the 4th minus 0.5 squared. And if you compute that on the calculator, you get negative 0.1875. So this is approximately negative 0.19. And then do the same thing for 1.5. So I'm going to plot a point in between the two zeros and then one to the right of that 0. So 1.5 to the 4th minus 1.5 squared, plug that in the calculator, you get approximately 2.81 to 2 decimal places. So now let's graph these points. So 0.5 to the right and negative 0.19. So let's see, this is negative 0.5, negative 0.25, about right here. And then let's see, 1.5 to the right, 2.8 up. So let's see here, 2.5, 6, about right here, 2.8. And then this has got y-axis symmetry. So for this point here, I've got a corresponding point on the other side of the y-axis. And then the same for this guy, I've got another one over here, about right there. And now we can connect these up here. So something like that. And of course these guys are going to keep going. And this isn't supposed to be straight. There should be a little bit of curvature there. It's just a little bit hard to draw here. So, but it's a W-shaped graph. And so this one goes up and turns back, and we see that it's got 3 turning points because it goes down, up, up. So it turns from down to up here, and then from up to down here, and then down to up again somewhere in here. Now it might not be right at 0.5 and negative 0.5. This actually might bottom out a little bit farther to the left here and farther to the right here. And in fact, that is what happens if you graph this on a calculator or with a graphing tool. You'll see that this is the approximate shape. And you actually need some calculus to find where those those little minimum points are there. Okay, number 8 here refers to the graphs and description for application exercise number 73 on page 379. And we're going to provide the following information. So we want to find and interpret f of 20, and how would this information be displayed as a point on the graph. And then we're going to use the leading coefficient test to determine the end behavior and ask if the function is useful in modeling. So if you look back at this problem, what it does is it gives you this equation here, and that models the worldwide tiger population X years after 1970. Okay, so that's this problem 73 on page 379. So you're going to be doing the same thing, but your numbers are going to be just a little bit different. So they ask us here to find f of 20 and interpret it. So f plug in 20 is just going to be 0.76 times 20 cubed, and then minus 30 times 20 squared, minus 882 times 20, and then plus 37,807. And you plug all of this into the calculator, and you will get approximately 14,247. So that's the estimate using the model. And then the actual, if you read the actual off of the graph for 1970, that value is 12,500. Okay, so this is an actual 12,500. Okay, and then they want to know how would you interpret f of 20? So this is going to be the tiger population. It's going to be tiger population in 1990, because that's 20 years after 1970. So that's tiger population in 1990. And then the actual, if you look up the 1990 population, you get 12,500. And then they want to know, is that an overestimate or an underestimate from the actual? And then by how much? Well, the estimation here is bigger than the actual, so it's an overestimate. And the amount of the overestimate is going to be the difference between those two. So it's the 14,247, and then subtract off your 12,500. And that gives you a difference of, let's see here, we want, yeah, and by how much? Okay. And that is actually 1747 is the overestimate. So if this would have ended up being less than the 12,500, then it would be an underestimate. And then our leading coefficient test here, we've got an odd exponent, and then our 0.76 is greater than 0. So that means that this model is not going to be useful, because if they're asking, if we don't use conservation here, if conservation efforts to save the tigers fail, okay, so that means that their population doesn't increase. Okay, because that graph, if you look at it, it decreases. And this portion of the graph that's estimating, that's a decreasing graph. It looks like this. Okay, and they want to know, well, if conservation fails, well, see, this graph turns around and starts going back up because it's a cubic graph. End behavior, it's got to go up here and down to the left, up to the right and down to the left. Well, if conservation fails, that population is going to keep going down instead of going up, going back up, and then it's not going to be a useful model past that time. But inside this time frame here, where the graph is decreasing, it does approximate pretty closely. Alright, next up here, looks like we need to do some long division here. So we want a quotient and a remainder dividing 4x cubed minus x squared plus 4x minus 1 by x squared minus x plus 3. So I go ahead and I put the dividend under the division sign here and the divisor out in front. And then remember, what we want to do is look at those leading coefficients and we divide them. So 4x cubed divided by x squared leaves us 4x, and so that goes up here in the x column, and then you do 4x times what's out in front, and then you bring that down here and you subtract. So 4x times x squared is 4x cubed. 4x times negative x minus 4x squared, and then 4x times 3 plus 12x. And then we want to subtract that. And so we want to do a subtraction here. And to subtract, we will change the signs and add. So minus, plus, minus, and then add. So 4x cubed minus 4x cubed, they cancel. Negative x squared plus 4x squared is 3x squared. 4x minus 12x, negative 8x. Then we bring this negative 1 down. And now we look at leading coefficients again. So 3x squared divided by the x squared will leave us 3. So that goes up here, plus 3, that's our quotient, 4x plus 3. Now 3 times what's out in front, so 3 times x squared, 3x squared. 3 times negative x here, negative 3x. And 3 times 3, 9. And we are subtracting that. So we're going to change the signs and add. So minus, plus, minus, change it to addition. So these guys cancel. Negative 8x, positive 3x is negative 5x. Negative 1 and negative 9, negative 10. So our quotient is right here. So we write it as the quotient, 4x plus 3, plus remainder over divisor. So minus 5x minus 10 over that divisor of x squared minus 3x. I'm sorry, minus x plus 3. And that one is all set. And let's see, number 10. Describe the steps for dividing the following two polynomials using synthetic division. So 2x to the fourth minus 3x plus 4x cubed minus x squared, and we're dividing by 4 plus x. So first of all, we've got to list these terms in descending order. So that's going to be 2x to the fourth first, and then 4x cubed, and then negative x squared, and minus 3x, and then we don't have a constant term up here, so we have to add a plus a 0. So remember, if any term is missing in here, you put a 0 term in. So if there was no x squared term, you put 0x squared in there. And then we're dividing by x plus 3. So remember the way this works. We change the sign of the constant in our divisor, so this is -3, and then we list the coefficients of the dividend, so that's 2, 4, -1x, -3, and 0. And then remember how the algorithm works. You bring the 2 down and you multiply by what's out in front, so this is a times. 2 times -3 is -6. That comes down into this slot here, -6, and then we add them. So 4 minus 6, -2, and then do it again. -2 times -3, +6, add, -1 and 6 is 5. 5 times -3, -15, add, get -18. -18 times -3 is 54. 0 and 54 is 54. So the 54 is our remainder, and then these are the coefficients in the divisor. So this is going to be the x coefficient, the x squared, and the x cubed. So our divisor then is going to be 2x cubed minus 2x squared plus 5x minus 18, and then plus remainder is 54 over divisor x plus 3. Alright, all set there. Let's see, got a rectangular box with sides h, 2h, and h plus 6. Use synthetic division again here to show that 2 is a solution of the polynomial equation. 2h cubed plus 12h squared minus 64, and I believe that's supposed to be equals 0. And so let's see, to show it's a solution, then you don't change the sign. So we leave that 2 on the outside, and then the coefficients here, 2h cubed, 12h squared. There's no h term, so we've got to put in a 0h, and then minus 64. And now 2 comes down, multiply out in front, bring the next column, add. So 2 times 2 is 4 here, 12 and 4, 16. 16 times 2, 32. 0 and 32 is 32. 32 times 2, 64. Comes over the next column. Negative 64 and 64 is 0. So the remainder is 0, so that shows that it's a factor. Okay, it's a solution to this equation equaling 0. That's the same as this 0 here. So that shows it's a solution. And then use the solution from part A to solve the problem. So we've got a width of a rectangular box is twice the height, and then the height is, the length is 6 inches more than the height, and then the volume is 64 cubic inches. So we got this box here. And we've got here the width is twice the height. So the width down here, so we've got height here, and then the width down here is twice the height, so that's 2h. And then the length here, it says is 6 inches more than the height, so that's h plus 6. And then the volume of this entire thing is 64 cubic inches. Well, volume is length times width times height. So that's length h plus 6 times width 2h times height h. Okay, so that product has got to equal 64. Alright, so now let's go ahead and multiply this out. So h times 2h, that's 2h squared times h plus 6 equals 64. And now multiply this in times each piece here. So 2h squared times h is 2h cubed. 2h squared times 6 plus 12h, and then equals 64. And now bring the 64 over as a negative. 2h cubed plus 12h minus 64 is equal to 0. And then we want to solve this equation. We want to solve for factors of h. Well, if 2 is a solution, that means that h minus 2 is a factor. Okay, and then this is going to be our quotient. This will be the numerical term, the h term, and the h squared term. So by that synthetic division, this factors as h minus 2, because see this polynomial here, it's the same one we started with here. So h minus 2, and then here's our quotient, remainder 0. So 2h squared, 2h squared plus 16h plus 32. And then notice we got a common 2 that we can pull out of there. So 2 comes out in front, h minus 2, and then we've got left h squared. 16 divided by 2 is 8, 8h, and 32 divided by 2 is 16 is equal 0. And then notice this guy factors. So this is 2 times h minus 2. It's a trinomial, so we can FOIL backwards on it. So h squared has got to be h and h. And then the 16, our first choice is going to be 4 and 4. And since we've got a positive 8h, we're going to do plus, plus. So then this tells us here that h is equal to 2. Or if h plus 4 equals 0, then h equals negative 4. But you can't have a negative 4 height, so this guy's out. So h equals 2 is our solution there. And then, let's see, that's going to be our height. And then our length is going to be 2h, which is 2 times 2, which is 4. And then our height is going to be h plus 6, so 2 plus 6. Our length, that's our length, is h plus 6, which is 2 plus 6. Length is h plus 6, 2 plus 6, which is 8. So we have got our height, and 2, 8, that was width, is what that was. Our width and our length. So we got all 3 dimensions there. And that's what we wanted, was dimensions of the box. So here we're referring to this graph, and we want to complete the following statements. So as x approaches negative 2 from the plus side, so you're coming into negative 2 from the plus side, your x values along here. What happens to the function value? Okay, so well, as you go up here to the function and over, to get closer to 2, go up and over, those function values are getting bigger and bigger. Or on that graph, if you want to, as you move on the graph closer and closer to negative 2, where we've got that vertical asymptote, this graph goes up higher and higher. So our f of x there, our function values or our y values, they're getting bigger and bigger. They are approaching positive infinity. As x approaches negative 2, that's negative 2 from the minus side. That's this one. F of x approaches plus infinity. And this first one is f of x is approaching negative 2 from the plus side, so negative 2 from the positive side here. And there, our function values, we've got to go down to get to the function. Our function is going down here to minus infinity. That would be a minus. X approaches 2 from the plus side, so here's 2. So we come into 2 from the plus side. You've got to keep going down farther and farther to hit the function and come over. So our function is going down to minus infinity. 2 from the minus side. So as you x values approach 2 here from the minus side, you got to keep going up higher and higher. Function's going to infinity. As x approaches infinity, so out here x gets bigger and bigger, our function values are coming up and they're leveling off here at height 1. This y equal 1 is a horizontal asymptote. So here f of x is approaching 1. And as x goes out to minus infinity, so as you keep going out farther and farther, big negative, come up to the function. This function is tapering off to height 0. So they never reach these values, but they get closer to them. So our vertical asymptotes are x equal -2 and x equal +2. Function goes to minus or plus infinity. Horizontal asymptotes are y equals 0 and the x-axis. Y equal 1 and y equals 0. Here would they want us to find vertical asymptotes, if any, of our rational function here, and then describe the steps to complete this. Okay, so they also want to know any values that correspond to holes. So let's take our function x plus 2 over x squared minus 4, a rational function there, and let's factor that denominator. So x plus 2 over, this is a difference of squares, x plus 2, x minus 2. So that ratio then is going to be equivalent to 1 over x minus 2. And we see that these x plus 2's cancel out. But this original function is not defined at -2. Okay, although this one is. The original is not defined at -2. So we've got a hole at -2 because that's the 0 for the factor that cancels out. So we've got a hole at -2. So that's here, x equals -2. And then our vertical asymptote is going to be at the 0 for the denominator here. When the ratio is a number divided by 0, then that ratio goes to infinity. So x minus 2 equals 0 implies that x equals 2 is our vertical asymptotes. Okay, number 14, we are finding a horizontal asymptote, if there is one, for this graph. And then we're describing the steps to complete it and providing answers. Okay, so our horizontal asymptote, remember what you do is you look at the leading coefficients in the numerator and denominator, and we see that they're both the same. They're both cube powers here. So that does have a horizontal asymptote that's equal to the ratio of those two. So a horizontal asymptote is going to be -4 over 2. Because remember why that is because as x gets bigger and bigger, these are what are called the dominant terms. So they're very big in relation to this minus x squared, so it doesn't make a lot of difference. So this ratio here, the ratio of -4x cubed over 2x cubed minus x is approximately equal to -4x cubed over 2x cubed as x gets bigger and bigger, and that ratio is -4 over 2, which is -2. So that's our horizontal asymptote. Remember, if the number, the exponent in the denominator is bigger, then the bottom it gets bigger faster than the numerator, and then the ratio goes to 0. So then your horizontal asymptote would be 0. And last problem here, we're using transformations of the function 1 over x or 1 over x squared to graph the rational function. This should be actually f of x is equal to 1 over x minus 3 squared plus 1. Well, this is the graph we're going to be starting from is the 1 over x squared function, and your 1 over x squared, if you graph that, it looks like this. This is x-axis, y-axis, and that's 1 over x squared. So it goes up to infinity at x equals 0. It's got x equals 0 as a vertical asymptote. So then, instead of x on the inside here, we've got x minus 3. So that negative 3 there, that shifts it to the right 3 units. And then the plus 1 on the outside is going to shift the graph up 1 unit. Okay, so our graph, f of x, which is 1 over x minus 3 quantity squared plus 1, is the graph of f of x equals 1 over x squared, and then you shift right 3 units, because remember, insides work as opposites, so negative 3 would be positive 3 units, and then the outsides work the way they're supposed to, and then up 1 unit. So instead of having a vertical asymptote at x equals 1, it's going to be over here at x equals 3. And instead of the x-axis being horizontal, we're going to shift it up 1, so then the line y equal 1 is going to be horizontal asymptote. So then that graph looks like this. Okay, and if you graph this guy in your calculator, you should get something like that too. Alright, very good. So this, you should be able to do homework problems from homework set 4 here. They should be very, very similar to these. So watch a problem, work a problem. Watch a problem, work a problem.